Hello there, team, and welcome to another update on Iceland and its evolving situation involving eruptions, magma intrusions, uplift, all the interesting things we've been watching over the past few months. Thanks for joining me. I'm Geology Professor Shawn Willsey. Today is Tuesday, July 9th. It is about 11:30 here Mountain Daylight Time, 5:30 or so p.m. over in Iceland. And we'll do just a brief update for today, not a ton to report. But then at the end of this update, I want to go over a paper, an older paper that Amanda Jo sent me with some of the borehole data from Svartsengi power plant that might help us understand the subsurface uh, architecture of the rocks and the geology that lies therein. So thanks again for joining me. Thank you for your support of the channel. Our community of interested learners is what really drives this thing and what makes us so special. So thanks again for joining me. Just a quick shout out to Amanda Jo, who is feeling quite ill right now. She was tested and she has COVID, but she is just really sick right now. And so I'm hoping she gets her quick recovery and starts feeling better soon. So we're thinking about you and hope it goes away quickly, Amanda Jo. So there's a new Met Office update for today, so I thought we'd start there. Not a ton of interesting, well, I wouldn't say interesting, but not a ton of impactful information here, but nonetheless, we have a new update, so let's just go through that. The land rise continues. I think that's the big theme for today is that the magma accumulation into that shallow storage zone beneath the power plant region is still going on. All the data is pointing to it. And assuming that continues, and there's no reason to believe that it wouldn't, then we would be likely to see some, magma movement either in the subsurface or at the surface as an eruption of lava within the coming weeks or so. How long that will take and exactly when that might occur can be extrapolated and forecast to some degree. But we're probably looking at several weeks, probably end of July, maybe sometime into August, until we see something that might be a little bit more imminent. And so they talk a little bit in here about. I thought it was interesting. They talked about earthquakes in here. It almost made it sound like as they mentioned the earthquakes in this update, and maybe I'm reading between the reading into this a little bit too much, but that it was notable. But according to and I didn't do a statistical look at this or anything, but I felt like the number of earthquakes that they talk about in this update is more or less similar to what we've seen in the past. So, in the past week, about 260 earthquakes across the whole peninsula, which might sound like a lot, but I think if we looked at just other periods of time in the past, years, even decades, I think that's on par with what you typically see. Deformation data shows that land rise is continuing at similar rates, and they did make us a little tweak to the risk assessment map. So there was a 1.3 west of Grindavik, but again, nothing notable. That's a fairly small earthquake, just a one-off, if you will. Some of those earthquakes of those 260 over the past week, not all of them in this area. Some are further east in the system that defines the Reykjanes Peninsula. And 100 or so were around Lake Klevravatten. And so kind of interesting. Again, most of these quakes are very small, not felt, low magnitude, and most likely related to the ongoing stress that accumulates across this divergent plate boundary. So none of those, I think, are indicative of magma on the move in the subsurface, because we need to see the earthquakes and the inflation, the ground deformation. Those two together are much more impactful and meaningful than just earthquakes in and of themselves. GPS data here, reading on, shows that land rise continues and has been at a similar rate for the past few days. Satellite image from June 25th to July 7th shows the same pattern. So they didn't show that satellite imagery or INSAR data on the update, but we'll go ahead and, that would be nice to see. But nonetheless, they've confirmed the GPS data and the INSAR data, if that's what they're using there, are both showing the same trend. So good correlation there. Model calculations continue to indicate magma influx is greater now than before the May 29th eruption. So we've got magma moving into the system at a slightly greater rate than it did previously. These data continue to indicate that another magma flow, either subsurface like an intrusion and or eruption, is likely in the coming weeks or months. And then they did a little tweak to the I won't blow this up, but basically they just modified slightly the risk assessment map and took out the power plant area because now they don't have the spillover. Remember, we had that lava spillover in that area, and so that's why they lowered it back down now that that lava flow is no longer an issue. So that's our Met Office update, brief and to the point, which is what we like. The earthquake data, predictably quite quiet for the most part. So here's Grindavik here. This is the area where we saw the past eruptions, and the only thing happening here are just a few earthquakes. These are all very low magnitude. In fact, these are negative magnitude earthquakes. A few around Fagradalsfjord, and then the typical clusters we've seen before in the Krishuvik system around Lake Krevarvat. And if we look at just in aggregate the past week or so, I know these dots are pretty small on this graphic here, but you can see there's that one 1.3 that was west of town, 4 kilometers depth. But again, none of this is very telling in pointing towards any sort of future activity. So this just seems to be business as usual across the Reykjanes Peninsula. And so they mentioned 200 or so earthquakes on the peninsula in the past week, and that probably shows a good number of them, if not all of those, more or less right there. So earthquakes, again, will be helpful as we get the system more filled with magma. And certainly if we see some trend take off here in the earthquake data that's a little bit out of the ordinary and anomalous, a new location, higher intensity, higher frequency earthquakes in terms of the numbers we're seeing, then that will be something we'll want to pay attention to. But right now it looks like the system is resetting itself just as it has for these last few eruptions that we've seen. Going on to the GPS data, excuse me, and we can go to Svartsengi station first and look at the uplift data here. So you can see the trend here after the May 29th eruption, mostly a deflationary trend as the ground fell a little bit. Again, this is an anomaly. If you go back in time, this is quite different than what we saw with the other ones. But then since then, it's behaved more normally with uplift since, I guess, what is that, maybe like after the first week or so of June, we've seen more steady uplift trend in the GPS data, and that would likely continue into the future. Now that we're into July, that's likely to continue through the rest of the month as we push towards late July into August. Who knows? Maybe we start getting to the point where the system is at capacity, starts pressurizing, and then we start looking at earthquakes a little bit more closely along with this GPS data to see if an eruption is about to take place again, or perhaps that magma finds a new weak spot in the subsurface and migrates some of that magma into that area, and we would see that with the earthquakes data most likely, in addition to a few other things. So that's the data for you. Again, not very, not a lengthy update in that sense, but I thought I'd also spend some time. Amanda Jo found some articles, some journal articles that I found a few of these, but she found more than I could have found, so that's great. On the borehole data and the subsurface data around the power plant, because I've been trying to wrap my head around getting a better image in my mind of the rocks, the type of rocks, and the characteristic of the rocks that this magma system is intruding into. I thought that would be just kind of helpful to do that. I think I at one point had the idea that I would put together a cross section, but lo and behold, in looking at some of this data she was able to find, some of that's already been done. So I may still do that, but if it's going to end up looking a lot like what was already done there, I may not. So what I've done here is I just want to go through one paper right now and maybe help you understand it. And I'll make sure this paper is in the links if you want to take a crack at it yourself. but I thought I'd start with the oldest one. She sent me several of them. So this is from 1983. And whenever I look at any sort of paper, it's a good idea to look at what journal it's published in, and then also like what it was, what's the purpose? You know, what was the intent or the aim or the goal of the author or authors here. So we've got this individual working for the National Energy Authority way back in 1983, the Svartsengi high temperature field, Iceland, subsurface geology and alteration. So that pretty much says it all. They are looking at the hot groundwater, this geothermal area, looking at its geology, but also looking at the alteration. So basically, as this hot water under Svartsengi has moved through the rocks, that hot water has also had uh, sulfur dioxide, different dissolved gases in it, and so there's been reactions with those host rocks and alteration. Those original basalts that were there when they erupted, now that they've had the hot water move through them, that hot water has maybe dissolved some material out. It's maybe precipitated or deposited different mineral material into the rock. And so that's what they're referring to when they say alteration. Um, and so like in the mining world, that would be something to be looked at with some scrutiny. So all these start out with an abstract, and abstracts are just a great way to get a full feel for what the general trend is. If you just reading the abstract first is a good idea because that will dictate whether you're interested enough to keep reading. If you just want to get a quick bite or sample of what the paper is about, this is a good way to go about it. So they are looking at the borehole data. I don't want to read it to you, so I'm trying to figure out how the best way to kind of tackle this with you. I think the best way to tackle this together, folks, is just maybe just lending a little bit of my insights here. You can obviously look at the paper and read it as well as I can, but maybe I'll just point to a few things that I found were helpful or noteworthy or things that might be a bit confusing that I can hopefully help clarify a little bit. So the abstract, I believe, is pretty straightforward. Then there's always an introduction if you're not familiar with the area or the geologic context in which the study took place. That's always a good place to start. In this case, we know quite a bit about this area of Iceland because we've been focusing on it for quite some time. And they talk about here, at this point in 1983, there were 11 geothermal drill holes. And they talk about their depths and the temperatures there, because obviously this is important for the power plant that was developed there and the geothermal resource. I believe this 83 date. I'm trying to remember now when the power plant came online. I'm pretty sure this predates this. So this would have been some of the data and information that was flowing and they were trying to characterize this geothermal resource better before they put in the infrastructure and developed it into, a power plant. They talk about how the permeability. So if you're not familiar with, and two words that actually do pop up in this paper to some degree is permeability and porosity. So permeability is how well water or fluid can move through the rock. And so that necessitates that there's fractures and pore spaces and openings, but they have to be connected, right? You have to be able to get from this void to that void. So you need connection between those pore spaces. And then porosity is just how much of the actual rock is actual voids, pore spaces, and in the terms of the rocks we look at in Iceland, that might be fractures, that might be little gas bubbles, what we call vesicles. It could be rubbly zones between lava flows where the rock has some pore space to it. So let's see, going on, they talk about, there's a little map here of the area. There's Grindavik, Svartsengi, so they've got some of the area mapped out a bit. Obviously crude, simple graphics because this is quite a long ways back in the early 80s. And then subsurface geology, and so based on the borehole data that they have, what the rocks in the subsurface look like. Mainly the rocks underneath Svartsengi are either lava flows, so superficial lava flows like the ones that just erupted recently in the area, or some of them are hyaloclastite formations which erupted during glacial periods. And so those would be, make that a little bigger for you. breccias. You've seen some of these rocks in some of the videos I've done in Iceland. So when when eruptions occur beneath glaciers in different periods of time in Iceland's past, those have been more explosive. You get the pillow lavas at the bottom, then you get this fragmented succession of rocks because it's being erupted more explosively as that ice is turning to steam or water vapor. That's a volume increase, and so it's expansive and it's breaking the rock up. So hyaloclastite you might think of as like a volcanic breccia. That would maybe be the best way to think of it. And then in general, the primary porosity and permeability at the intersection of the lava flows, as well as within the hyaloclastite formations, are considered to be quite high. So it's a good place for a geothermal system to have hot water at depth be able to move through the rock, get close to the surface without losing a lot of its heat as it moves. They do mention here, going on to I guess the next page, that intrusive rocks aren't really found above 700 meters, but once you get it below 800 meters in these boreholes, there's a lot more intrusive rocks. So instead of magma that erupted at the surface, this would be magma that was injected into the subsurface and cooled and solidified in the subsurface. And so intrusives increase to about 20 to 40% of all the rock once you get below about 800 meters, which is interesting. So that's going to affect how the groundwater can move through it. That's why I think you generally have this geothermal system closer to the surface than at depth per se. Let's see, what else do we have here? Then here we have a map showing some of the boreholes. You can see like S11, S7. So all the black dots are the different boreholes that they had at the time. I guess they did have the power plant because it's right there on the map. So maybe it was just in its early stages or something at that point. And then there's a cross-section line here from A to B. So they have reconstructed a cross-section. So the idea here, and I used to do this all the time when I did groundwater work before I started teaching, is they've taken the well logs of these boreholes. And so you can see S9 and S6 are right along the cross-section line. Well, you take the ones that are close and you just project those into the cross section. So you can see S9 is here, S6 is way over there, and you don't know, effectively you don't know what the geology is like between those 2 points, but you have S7 here, you have S4 here, and so you just take the borehole information for those 2 wells and project them onto the cross section, so you have more data points as you work across the cross section there. The black lines here with the little tick marks are the location of faults that they believe exist based on the cross-section, which I'll show you here in a second as well. And so let's go right to the cross-section, which means I have to rotate this around and maybe make it a little bit smaller still. So mainly focus on the one on the left here. So there's A to B, so there's that more or less east-west cross-section line. And then you can see all the boreholes, right? There's borehole 9, 11, 7, 8, 4, 5. So they projected basically all the boreholes onto that cross-section line, which is a little bit, it's all you have are these boreholes. But the further you're projecting that borehole's data onto the cross-section line, the more tenuous that interpretation is. So remember, when we see a cross-section like this, a subsurface cross-section based on subsurface data like boreholes, it's an interpretation, especially between the boreholes. The boreholes, if they've been logged correctly, that's data, that's facts, right? That's the truth at that location. So if you go down borehole 9, these are the rock types you encounter. But what happens in between these boreholes on this cross-section is the interpretation of the geologist who constructs the cross-section. So you could give this task to several geologists, and it's possible, well, it's very likely you would end up with some slightly different cross-sections. Hopefully, in general, they show some of the same general themes and trends, but it's very likely that they're a little bit different because it's a bit of an interpretive process. But nonetheless, it's the best thing we have conceptually to seeing what's going on in the subsurface. So basically what they've done here is broken up the rocks into 2 types, which is a good way to approach this. The basalt that is lava is shown with this white kind of dashed line here. And then the kind of gray area here, again, 80s graphic design here, is hyaloclastite. So basically, this gray color would be uh, eruptions that took place in glacial conditions, and then the white stippled pattern would be eruptions that took place when ice was not present on the landscape. And so you can kind of see the differences here. And then what they've tried to do as best they can is, in borehole number 9, you've got so many meters of hyaloclastite, then you go into lava. Well, then you go into the next borehole over, and you try to match things up. Now, things obviously don't match up perfectly across here like a layer cake. And so where there is considerable shifts or places where there's offset there, that's where they're trying to invoke faults. Like, well, these two don't match up, but they should. So the most acceptable reason why they don't match up is somewhere between these two boreholes, there must be a fault that has shifted things up and down, which is a good way to go about it. It's a bit simplified to assume it's just one fault that's accommodating all that offset, but it's the best you have to go on. And the cross-section ultimately should have, the most simple, straightforward solution that allows the borehole geology, which is the real data, the real facts, taking that data and then trying to match it to all the boreholes. So you're trying to put together a cross-section that makes sense for everything here. So anyway, so they've got some of that here. So you can see the cross-sections. These black lines here, these are the faults. So they show the up and down motion there. And again, it just gives them a handle on just characterizing the system in the area and what's going on there. So, and they even say right here, a simplified geological cross-section. They're not saying this is the exact truth. They're not saying if you drill down right to that spot, that's where that contact's going to be. This is just the best explanation we have based on the data. Notice over here it shows intrusives very scarce, and then you get below that 800 meter threshold, and intrusives are a little bit more common. But for whatever reason, they didn't really show those on here. I have seen other cross sections in this area that actually do depict the intrusions. And I think as we get to some of the more recent papers, excuse me, we'll kind of see this. And I think what would be neat for you folks to see and understand is how, these early papers and diagrams with more limited data, fast forward 40 years and you'll see sort of the evolution of things. You'll see how more detailed they are in, putting some of this information in there. So anyway, so there's that, and I don't want to be too long-winded with this. Let me rotate things around. Excuse me. Then they talk a little bit about aquifers and hydrothermal alteration. Obviously, they care about that because they're sort of characterizing this geothermal system. I won't spend too much time on that, but they're looking at places where when they're drilling down and they lose circulation of the mud, that's usually because it's lost to the rock itself. So that indicates that there's much higher permeability there. If you're drilling through very solid rock, then you're able to maintain the mud that is cutting through the rock. But when it goes into a very permeable layer, that mud will be lost into the formation, and the driller has to kind of deal with that. And so that's usually indicative of, some of the groundwater and permeability issues that are down there. So anyway, so kind of a fun paper, discussions and conclusions, acknowledgments, that sort of thing. Anyway, so just kind of walking you through the paper there. Hopefully that was helpful. I will be out the rest of the week, but I'll have a couple more videos out that you guys can watch. And with that being said, I know these Iceland videos get the most views and are of the most interest to the majority of you, but I would encourage you to still watch some of the other videos I put out. If you're just interested in geology in general or volcanoes, I think you can learn a lot, even if it's not a place you feel like you're interested in. Rocks are rocks, and so there's a lot to be learned by just learning geology from one place, and then you might be able to take that and apply it to your area of interest. So just thought I'd put that out there. It's just it's all good stuff, and there's other people putting good stuff out there as well. So thanks for your time. Hope this was helpful, and we'll see you next time. Take care, team.